Let me allow. Yes, I think you can share.
It should be visible.
Yep.
So yeah, basically what I understand from linear algebra and what I think of it is as it's a system of representing something, especially the linear equations in matrix forms and also some vector spaces. And we can implement this on quantum systems and other things. So first of all, let's start from the simplified section. So the systems of linear equation, we're gonna turn it into a matrix. So if we have two equations like a11x and a12y, here a11 and a12 are constants, the coefficients of x and y. B1 is also another constant. The same goes for the second equation. We can form a matrix and write it in this manner, showed in the 1.3 our equation. I think I might draw, that would help a lot. And for simplification, we can change the y and we can also present it as x2. This is the most simple form of presenting linear equations in matrix forms. And what are the benefits of this? We can solve some bigger sets of equations pretty easily with that. Let's say here we have only two variables. For like say 5 to 10 variables, we would have had like 5 to 10 equations. Then that would have been a much hectic to solve. So we can rather transform them into matrices, and then we can perform eliminations like Gauss elimination and Gauss-Jordan and solve the matrices and get the solutions for the linear equations. And here, say, from this, we can also write from 1.4. We can write this as x1, and x1 is multiplying with the matrix A11 and A21. Here we can call it a vector space and can write it as, let's say, we can write it like a vector u. In a matrix form, we can write, say x1 and x2. Let me just avoid x, and because we're using that this variable, let's say a and b. And we can also write it down as Dirac notations for quantum mechanics. The Kate notation. So first of all, uh, these are the representations of multiple things in matrices form. That is the basic of linear algebra. And we're going to use these simplified implications to solve complex problems. So the first section was solving system of linear equations using matrices. We can do plenty of other things using this. And as I previously mentioned, we can solve the matrices using Gaussian elimination, Gauss-Jordan, and also determinant method, which might be quite hectic to solve using determinant method. Gauss-Jordan and Gaussian elimination is much easier. Now moving forward, we can form eigenvalues and eigenvectors to solve some complex problems. So what are eigenvalues and eigenvectors? Let's say we have a matrix A and we multiply this matrix with a vector X, this manner. If the vector gives a value, a scalar like this, and the vector doesn't change, we can call this a eigenvalue and the vector x is a eigenvector. And this eigenvector, what does this lambda do? This eigenvalue, what I'm calling, what this does is actually, this is a, how can I put this? The scaling factor. I can call it as a scaling factor of the vector x. And one thing I missed actually, should have mentioned previously, like putting a vector as a matrix. Actually, I mentioned it, sorry. Previously mentioned we can write vectors like this in the matrix form. So eigenvalues and eigenvectors are pretty amazing things. We can, uh, for say, we have like observables in quantum mechanics, like Hamiltonians and other things. From that we can get values of observables. We need to calculate those. So from the concept of eigenvalues and eigenvectors, we can solve those complex problems. So for say, we have here Ax, here x is the eigenvector and lambda is the eigenvalue. We can also write it down like Ax lambda I x, which is a identity matrix. And we can then shift this whole thing to the left-hand side, and we can write it like A minus lambda I, taking the x vector common, which equals to 0. Here x can be or cannot be 0. Since it's a vector, we cannot just say the value of x can be 0. So the coefficient here, this must be a singular matrix. And here why I have taken the identity out of x, because x was a vector and we cannot just subtract a vector from a matrix. So we have taken the I out of this identity. And we can come to the decision that this should be a singular matrix for the whole thing to be 0. So we can write it like A minus lambda I. This should be equals to 0. And the value of this can be calculated from the determinant of it, which should be equal to 0. And what we get from here, we can actually calculate the eigenvalue for the eigenvector x from this equation. So here's a simple example of that. We have a matrix A, and we are about to calculate the eigenvalue for this matrix. So here simply we have taken the determinant and eventually solving for lambda, we've got two values. One is -1 plus I root 3, and the other one is simply the conjugate of this complex conjugate. Then in the next section, we're going to talk about the normalization process. And what is normalization? In simple terms, getting the magnitude of a vector is basically normalization. And we can do that even over the vector matrices. If we have like we have a vector like, let's say, u equals to 1 and u2. We can normalize these vectors and get the value out of it. And we must always remember that these are column matrices actually. The basis of the vectors will be something like this. Let's say A, B, A1, B1 for the first one. And let's say for the second one, A2, B2. And if we put some real values for this, let's say I can have 1 and 2, say 3 and 4. Then normalizing this would mean for first one, say vector u, normalizing would be like dividing it with the values here. And what we will get is so that was for the normalization section. And next we are going to move to the diagonalization of matrices. We're going to also discuss why this is important. So simply diagonalization of a matrix means converting a matrix into a diagonal matrix, which is necessary for multiple cases. Most common one would be solving the power of matrices. If we have like A square, we can calculate A into A, which is still much simplified, easier one. But if we have like A to the power 10 or something much bigger than that, then we can diagonalize the matrix and then calculate later. So if I demonstrate a bit, say let's say we have a vector space, which is U, and the values of it are U1, U2, and eventually, if we expand these columns, we will get, let's say, 1 minus 3, and say 1 power minus 1. Suppose this is simply a matrix, and in normalized form, we will get the magnitude of it. I'm not going to write it for now. Now, suppose it's just a matrix U, which will diagonalize the matrix A. The question is how? Here U1 and U2, let's say these are eigenvectors. These are eigenvectors for the matrix A. So if we say like A U1, then we will get something like lambda1 U1. Here lambda1 is the eigenvalue. And for the U2, we will get like U2, then lambda2, U2 is the vector, sorry. And if we say we have both together, say A U we will simply have lambda1 U1. Let me clear this up a bit. And lambda2 U2. From here, what we can do is we can expand them in matrix form, and we can write it like U1, U2, here. So here we are using a matrix U, which contains some vectors, which are eigenvectors, and we are converting the A matrix into a diagonal matrix. Here, lambda 1, 0, 0, lambda 2 is a diagonal matrix. And we can call a diagonal matrix, say, here we call this as the capital lambda. And if we have like multiple, say we have U3 here, we will get a 3 by 3 matrix of eigenvalues. And for 4, we have like 4 by 4 matrix of eigenvalues. And now from here, clear this a bit. I'm a bit slow with my mouse.
No, it's okay.
Usually don't.
Yeah, it's difficult to write with the mouse, I know.
Yeah. Now I can put this eventually as AU sums up as U lambda. And what I can do is now, if I multiply the inverse of U, which is U inverse 1, from left, I will have U inverse A U, and this U will get cancelled. This, and we will be left with lambda, which is the diagonalized matrix of a diagonal matrix. I'm sorry, not diagonalized matrix. You can write it as U inverse A U. And we can use it to calculate the power of a matrix. I'll be showing that right away. And this is what I've previously discussed at the beginning. We can write down the matrix in different bases. Oh, no, I haven't mentioned this before, sorry. We can write down a vector in actually different bases. So for Cartesian coordinate system, let's say we have a vector R, and we can write it like this way. So write this like X I cap, Y J cap. Let's say for 2D system, I'm not gonna go to the 3D. It's quite same actually. So here are the bases. The bases are I and J, which are Cartesian bases. But for eigenbases, instead of I and J, we are going to represent a vector with vector eigenvectors. So let's say we are presenting R instead as equals to, let's say, X to a vector, let's say U, and it's 2. I should write Y. Actually, I shouldn't have written X and Y because it's not necessarily in Cartesian plane, but yeah, this. And since these are columns, we can also actually write this in direct notation forms, and or like we can write quantum mechanics, we write it like, let's say, X and U1 plus Y U2. Now let's move to the power of matrix. So previously we have had UA U inverse 1 is actually lambda. So getting the power of A and solving it for like higher level of powers is quite hectic. But since lambda is just a simple diagonal matrix, we can put any power above it and we will have like, say, for lambda 1, lambda 2. If we have the power of 2, we will get lambda 1 square. Actually, it's going out of my screen. Okay. I'm actually writing here on this actually. Let's say we will have like lambda 1 square and lambda 2 square this way. Now, using this idea, you can actually calculate the power of matrix. Let's say we will have here for a to the power n, we will have u a to the power n, u inverse 1, and lambda to the power n, which is much easier for us to calculate as I previously mentioned. We like select this side. So now what we can do is we can multiply u inverse 1 from the left, which will cancel out this u. And we will have u inverse 1 lambda n. And again, we can multiply u from the right. We will have u inverse 1. And then again, these two will cancel each other out. U inverse 1, lambda to the power n, and u. And eventually, we get to the point that a to the power n is equals to u inverse lambda to the power n u, where lambda to the power n is simply the diagonal matrix, which is much easier to calculate. And these were some applications of linear algebra. And then again, we can use matrix as transformation operators. Here, the A is a matrix, and let's say the alpha V and beta W is a transformation operator. So if we compute this, here alpha and betas are scalars, and A is a matrix, V is a vector. So we can calculate it in this way, and we will solve some complex problems with these concepts. And that was all actually. I'm not really good at linear algebra, but I have tried my best. This, I think there might be some wrong assumptions which are made by me, and I am not very good with the terminologies. There might be some problems with that as well. So yeah, that was it. Thank you so much.
Yeah, thank you, Alvi. The presentation was good. But I think between different, so when you presented linear equations and went to the matrix form, sometimes when you transition between one concept to another, sometimes it's good to have a gap, like, let the audience think for a few seconds, right? And then move on. That could be one improvement. And I think if you had those vectors drawn in the LaTeX document, like beforehand, right? That would have made things a little easier, right?
Oh yeah,
So yeah,
would
that
have been easier.
yeah, মানে
So,
I mean আগে থেকেই ড্র করা আছে, uh, like we can represent vectors in many ways. One way is uh, in a diagram with an arrow in XY coordinate system, ওর জন্য যে বেসিস ভেক্টর তাকে আমরা আই হ্যাট জে হ্যাট বলতে পারি, ওকে কলাম দিয়ে রিপ্রেজেন্ট করতে পারি। দেন একটা ম্যাট্রিক্সের মধ্যে ইউনো matrix A equals two columns, one represent x hat direction, another one j hat direction, right? এই ছোট ছোট জিনিসগুলি জাস্ট একটু অর্গানাইজ করলে আই থিঙ্ক ইউল ডু মাচ বেটার।
Yes, I'll correct those on the LaTeX
ওকে
hopefully
ওকে
in
ইয়া,
future.
এখন যেটুকু বললো না যে লাইক মাঝে মাঝে এক্সপ্লেন করার সময় ইউনো মাঝখানে দু একটা লাইনগুলি লেটেক্স ডকুমেন্টে ছিল না, তুমি লাইন লিখে লেখার চেষ্টা করছো, রাইট? সেইগুলি অর্গানাইজড ওয়েতে লেটেক্স ডকুমেন্টে লিখলে আই থিঙ্ক একটু আর মানে আরো ইমপ্রুভ হবে ওই ডকুমেন্টটা। হ্যাঁ।
Okay.
ওকে, এনি কোয়েশ্চেন্স ফ্রম এনিওয়ান এলস? ওকে, সো আলভি যেটা প্রেজেন্ট করলো সেটা হচ্ছে আমি যে ওভারলিফ ডকুমেন্টটা দেখিয়েছিলাম, আহ, ও আমাকে যখন ওর ওভারলিফ ইমেল অ্যাকাউন্ট সেন্ড করলো, তখন ওকে বললাম যে ক্যান ইউ ডু দিস, লাইক ইমপ্রুভ দ্য নোটস অন লিনিয়ার algebra a little bit, then you present. So he was the first to share his overleaf email. Thank you. And সো নেক্সট উইকে আমরা যেটা করব, ইউনো যারা এখনো প্রেজেন্ট করে নাই ওদের মধ্যে কেউ না কেউ একজন প্রেজেন্ট করবে। ইট কুড বি এনিথিং, ইট কুড বি সিম্পল। ফর এক্সাম্পল, কোয়ান্টাম এসপ্রেসো যে স্টেপগুলি আমরা রান করেছি সেইগুলিও তোমরা দেখাতে পারো প্রেজেন্ট করার সময়। এক্সপ্লেন করবা যে হোয়াট ইউ হ্যাভ ডান, লাইক হাউ থিংস আর ডান, লাইক ইন ইউর সিস্টেম অর ইন দ্য সার্ভার। ওকে, ইনপুট ফাইলটা কিভাবে লিখবা, অর পিডাব্লিউটি কে এটা কিভাবে ইউজ করে আমরা এটা রান করতে পারি। এরকম লাইক আই নিড ভলান্টিয়ার, আমি অ্যাসাইন করতে পারি, বাট আই নিড লাইক ভলান্টিয়ার যে হ্যাঁ আই হ্যাভ টাইম দিস উইক, আই ক্যান প্রেজেন্ট। হ্যাঁ, তাহলে আই থিঙ্ক আমাদের প্রোগ্রেসটা একটু ভালো হবে। লাইক ইউ প্রতি সপ্তাহে একজন যদি প্রেজেন্ট করো, ইটস প্রবলি গুড এনাফ। প্লাস আমাদের ডিসকাশন চ্যানেল আছে ডিসকর্ডে, ওখানে আমরা ডিসকাস করবো বিভিন্ন জিনিস। প্লাস আজকে যে প্রেজেন্ট করলো আলভি, ওর জন্য আমি একটা গুগল ফর্ম তৈরি করেছি, ফিডব্যাক ফর্ম। মানে হচ্ছে এটা আমি শেয়ার করব, আই থিঙ্ক এখনই শেয়ার করি, জাস্ট এ মিনিট। এটা কাইন্ড অফ অ্যানোনিমাস ফর্ম, doesn't collect any email, so just you can say be constructive. Okay, so এটা আলভি প্রেজেন্ট করেছে, সো বাকি যারা আছে ওরা লাইক গিভ ফিডব্যাক হাউ টু ইমপ্রুভ। আর এই ফিডব্যাক গুলি আলভির সাথে শেয়ার করা হবে, বাট উইদাউট এনি নেমস, অ্যানোনিমস। ওকে, লেট মি শেয়ার দ্য লিঙ্ক। ইয়া, আমি জুমের চ্যাটে শেয়ার করেছি। Yeah. So, things to improve, what you liked, what you didn't like, few things, just anonymous. Okay. My personal opinion is uh, feedback is a good thing when it's constructive. Okay. We all want to improve, right? How do we do it? We take feedback from the community and practice, and we improve. Okay. Any questions from anyone? অলরাইট, লিনিয়ার অ্যালজেব্রা যে আলভি প্রেজেন্ট করলো, এখানে কারো কোনো কনফিউশন যদি থাকে উই ক্যান ডিসকাস। ওকে, আলভি তোমারও যদি কোনো কনফিউশন থাকে কোনো জায়গায়, ইউ ক্যান আস্ক, উই ক্যান ডিসকাস লিটল বিট।
আমার অ্যাকচুয়ালি টার্মিনোলজি গুলো নিয়ে একটু প্রবলেম ছিল, আমি কিছু কিছু জায়গায় ভুল বলেছি আমার মনে হয়। আমি নিশ্চয় আগে পড়ে দেখতে চাই। আহ, আপনি যে হচ্ছে লেকচারটা শেয়ার করেছেন, আমি ওটা একটু দেখতে চাই, তাহলে আমার মনে হয় ভালো হবে আজকে ডিসকাস করার আগে।
ওকে ওকে, ঠিক আছে,
Well,
we can discuss them later, it's fine. আহ, তাহলে ওকে, সো তাহলে লেট মি শেয়ার মাই স্ক্রিন। লিনিয়ার অ্যালজেব্রা আলভি আজকে প্রেজেন্ট করলো। সো আই থিঙ্ক ল্যাটিস ভেক্টরস, রেসিপ্রোকাল ল্যাটিস ভেক্টরস নিয়ে কথা বলবো বলেছিলাম। ওই ফ্র্যাকশনাল কোঅর্ডিনেটস অ্যান্ড হাউ টু কনভার্ট ফ্রম কার্টেসিয়ান টু ফ্র্যাকশনাল কোঅর্ডিনেট। ওই কোয়ান্টাম এসপ্রেসোতে ফ্র্যাকশনাল কোঅর্ডিনেট ইউজ করা হয়। সো হোয়াট আর দোজ থিংস? সো এটা নিয়ে একটু ডিসকাস করা প্রয়োজন। সো লেটস স্টার্ট উইথ দ্যাট। লিনিয়ার অ্যালজেব্রা উইল হেল্প হিয়ার অ্যাকচুয়ালি। সো okay, yeah, you can leave, but it will be recorded so you can watch it later. Let me share my screen on my iPad. Just a minute. Uh, okay, join. Uh, okay. Uh, I think. Wait a minute. It's not here. Um, Meeting ID. I need the meeting ID. Okay. 983 3629 3288. I think you can. Okay, I think you can share my see my screen. Let me okay, let me have the document open. Okay, so let's start. Uh, so how do we represent vector? Uh, any vector v can be represented like this, a column 2, 2, 3, and in the in a Cartesian coordinate system diagram, it will be this is if this is x hat, this is y hat direction, then this means 2 step along x hat and 3 step along y hat, and the vector would be this one, right? This is the vector v. That's how we represent a vector. Okay, and we have in a lattice we have lattice vectors or primitive lattice vectors. We call them a1, a2, a3. Okay, so these are for cubic system. A1 is basically along x hat direction, A2 is y hat, A3 is z hat, and their coefficient is just A for cubic. For different kind of lattice, A1 could be A x hat and you know A2 y hat, a little bit complicated. But the idea is we have 3 lattice vectors, primitive lattice vectors, A1, A2, A3, and we can construct um, a vector R like this, N1, A1, plus N2, A2, plus N3, A3. And this n1, n2, n3, or ni's are all integers. This z means integer. This is a mathematical symbol for integers. This r is called uh, the lattice vector. Uh, okay, general lattice vector or translation vector, or in real space. What do I mean by real space? It means, you see, A1, A2, A3, they have the units of Armstrong or meters in SI unit, meaning their displacement or distance in meters, in real unit of distance. So that's why they're called, in real space. And we also have something called reciprocal lattice vectors. So how do we construct them? I think I have discussed it before a little bit. So primitive uh, reciprocal lattice vectors. B1, B2, B3. How are they defined? B1 is A2 cross A3. B2 is A3 cross A1. B3 is A1 cross A2. And as a factor, we have 2 pi over V. 2 pi over V, 2 pi over V. And V is the volume of the unit cell, which is A1 cross A2 dot A3. That's the volume of unit cell. Okay. These are the primitive lattice vectors in reciprocal space. Reciprocal space কেন বলছি? Because if you find their unit, they have inverse Armstrong unit. কারণ হচ্ছে, you see, A1, A2, A3, they are in meters, for example. V is meter cubed. So if you divide meter squared over meter cubed, you have 1 over meter, 1 over unit of distance. So they have the inverse Armstrong unit. Armstrong হচ্ছে 10 to the minus 10 meter. 1 Armstrong is 10 to the minus 10 meter. It's like atomic distance unit. Okay. All right. From here, well, we have A and B, right? They have a orthogonality relation, which is AI dot bj equals twice pi delta ij. Meaning, if you do A1 with B1, you get just twice pi. We can prove it. So what is B1? B1 is 2 pi over V A2 cross A3, right? Left hand side. Then 2 pi over V is a constant. We have A1 dot A2 cross A3. And notice this is nothing but the volume of the unit cell, V, and V cancels out, we get twice pi, which is the right hand side. Does it make sense? Any questions? Okay, so we have lattice vectors, we have reciprocal lattice vectors, and we also define something called the translations in the reciprocal space, or the general reciprocal lattice vector G, which is M1 B1 plus M2 B2 plus M3 B3. Notice one thing, here, what is R? R is nothing but a linear combination of A1, A2, A3. Combination of A1, A2, A3, right? Does it make sense? Linear combination মানে হচ্ছে প্রত্যেকটা ভেক্টরের সাথে একটা স্কেলার দিয়ে গুণ করব, then we add up all the vectors. And here G is again linear combination of B1, B2, B3. M1, M2, M3 are just numbers. Here they are integers, right? And we can write M equals M1, M2, M3 like this. Sometimes they are written like this, H, K, L, and these are called Miller indices. Okay, this name is important, plus it's useful when you, you know, when you do X-ray diffraction, for example. Okay, because so we can write uh, G H K L H B1 plus K B2 plus L B3. And the norm of HKL, norm of G, is equal to twice pi over D HKL. Okay, I mean, এটা নর্ম বের করলে যা পাবো তাকে যদি আমরা এইভাবে ডিনোট করি twice pi over D HKL, then the Bragg's diffraction law uh, becomes 2D sine theta 2D HKL sine theta equals n lambda. মানে হচ্ছে this D is the spacing between layers, Bragg planes. Okay, X-ray diffraction, if you remember, we have atoms or lattice sites arranged like this, right? And X-ray comes like this and gets reflected here. Other one comes like this, gets reflected here. And there's this spacing is, say, A, lattice spacing. It's a cubic system. Let's say this is also A. And or we can call it D. Okay. And this is D. And the angle of this angle of reflection or incident is, say, theta, then if that's theta, then this is also theta. And if that's theta, then I think these are two parallel lines. This is also theta, right? That means, okay, I need different color. This line is, no, not this line. This line here is d sine theta. Okay, and so we can also have some d sine theta here, right? So what's happening? Two parallel rays are getting reflected, and this is ray 1 and this is ray 2. They're traveling different path length. One path is traveling 2d sine theta more than the other one. And if the difference, if 2d sine theta is equal to n lambda, then we get then they superimpose with each other and make a constructive interference. What do I mean? So this is a wave, right? And this is another wave. And when they meet like this, their uh, nodes uh, align themselves in between two waves, then if we sum them up, when they meet together, they create a constructive interference there. Okay, so you get a peak if they're aligned, and if they're misaligned or aligned by you know aligned like this, like maximum of one wave is aligned with the minimum of the other wave, then you get a destructive interference, basically flat line. What happened? Okay, a destructive interference. So if the path difference 2D sine theta is equal to n lambda, then you get constructive interference. So that raises to the Bragg's law, and so that's related to the reciprocal lattice vectors in this way. Okay, just a side note to have it in mind that when you do Bragg's law, X-ray reflection, scattering, these things are there, and this is how they are kind of related. Okay, so back to where we were. So G is the reciprocal lattice vector, and I think I also mentioned something, you know, the fractional coordinate, uh, or yeah, the fractional coordinate. So in reciprocal space, meaning 1 over m inverse Armstrong unit space, where we have b1, b2, b3 as unit vectors, we can write the k point like this. I think we use u b1 plus v b2 plus w b3. It's similar to G, but a little bit different. And notice here for G, HKL or M1, M2, M3, they were just numbers, dimensionless numbers. Okay, and that's how we got the Miller index. For reciprocal space, for a K point, U, V, and W, they are also numbers, but they're uh, not integers but fractions. U, V, W, their range is 0 to 1. Okay, meaning so what does it mean to have range 0 to 1? If uh, when their range is 0 to 1, then what is k? You can move in any direction with k by changing u, v, and w. If the range যদি 0 to 1 এর মধ্যে হয়, তার মানে হচ্ছে if you are moving along b, then either you are here or there maximum here. You cannot go beyond b1. মানে let's say for example v and w is 0, then the k point vector, k vector is just u b1. আর u হচ্ছে 0 থেকে 1 এর মাঝখানে কোনো একটা ভ্যালু, right? So if u is 0, then k is 0. You are at the origin. If u is 1, then you are here. If this is the b vector, b1. If u is half, then you are here in the mid, in between. দ্যাট মিনস এই বি ওয়ান ভেক্টরের যে কোনো পয়েন্টে তুমি যেতে পারবা, এর বাইরে যাওয়া পসিবল না। ডাজ মেক সেন্স লিটল বিট? মানে এখানে যে ইউনিট সেল তৈরি করলাম না, ইন 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 real space a1, a2, a3, we get a cube, right? The the unit cell, reciprocal space এ reciprocal unit cell আছে, right? যেখানে for example say this is also a cube but এদের length গুলি হচ্ছে b1 b2 and b3. With this k vector we can move around inside this unit cell in reciprocal space. এর বাইরে যেতে পারবো না, meaning we are always inside the first b1 zone. Okay, what is the b1 zone? Probably it was the first or second lecture we discussed. Okay, so that was basically, I remember the dispersion relation E of k as a function of k. We went from minus pi by a to plus pi by a, right? To plus pi by a. Uh, let's say this range. So you we've seen the phonon dispersion relation, right? It goes like that. So this range is called the first B1 zone. Remember, it was from the probably first or second session. Meaning with this k vector, we are always inside the first B1 zone. কারণ হচ্ছে UVW কে আমরা ওইভাবে restrict করে দিয়েছে. Okay? Does it make sense? Any question? Okay. Um, Now the question is how we can go from uh, uh, fractional coordinate to so what is the fractional coordinate? That's important. Fractional coordinate is basically এখানে যে u v w ছিল না, we construct a vector using them u v w. That's our fractional coordinate. Okay, if these are 0, that means we are at the center of the Brimon zone. If they're 0, 0, 1, that means we are so W is with B3, right? So along B3 we're here. Okay, and 0 along B1 and B2. So with these fractional coordinates we can find where we are in the unit cell of the reciprocal space, okay? And sometimes we need to convert between fractional coordinate to the k vector. And the way we do that, let me share my screen, the other screen. Stop share, stop broadcast. Desktop 1. Can you see my screen?
Yes, sir, we can see.
Okay. So here I try to write a summary like real space lattice vector, reciprocal space vectors, and here I have the transformation. So B, if you notice the columns of B, this is just B1 vector, and this is B2, and this is B3. If you have the fractional coordinate K and you multiply that by B, then you go to the Cartesian coordinate. And if you want the fractional coordinates from Cartesian, you just multiply with the inverse of B. This is exactly the transformation that Alvi was presenting today. Like if you have a vector, you multiply with a matrix, you get a different vector, or you transform the vector. Okay. So K frac is just this M1, M2, M3 but they're limited to range from 0 to 1. Okay, does it kind of make sense? Because these are important when you want to find the k-path. For example, yeah. So uh, my notations are consistent here, which is a problem. So that's why I need someone like all of you to proofread this document and make the notation consistent, okay, with one section to another. হ্যাঁ, for example, এখানে দেখো যে the k vector is written like this: u1 b1, u2 b2, u3 b3. u1 u2 u3 are the fractional coordinates. In fractional coordinates, they are the gamma point 0 0 0, the center of the reciprocal unit cell. The x point is 0.500. This is like standard definition. মানে u1 টা হচ্ছে 0.5, u2 0, u3 0। তার মানে কি? তার মানে হচ্ছে along b1 direction we go halfway, along b2 and b3 we don't move at all. That's our k vector. এটা হচ্ছে fractional u1 u2 u3, that's the fractional coordinate, and in Cartesian coordinate that will be u1 times b1. So another way of saying fractional coordinate যে নাম্বারটা থাকবে u1 u2 u3, if you take those numbers, multiply by b1 b2 b3 vectors correspondingly, you get the vector in the Cartesian coordinate or inverse Armstrong coordinate. Does it somewhat make sense? Okay, so এটা important কারণ হচ্ছে, if you remember, let me show it here. So this is our document. এখানে আমরা অনেক কিছুই কিন্তু অ্যাড করছি রেগুলার। So that's why I need your overleaf ID so that you can proofread. It's also a document. Just যেটা শিখবা নতুন, like it could be useful. You just add it here. Uh, okay. So uh, here I think I have the code here somewhere. Yeah. So if you remember, in our input files, we have the k points list. 0 0 0, we call it gamma. 0.5, right? Where is the PWTK? Okay. We have this k point in SCF and NSCF computation, where we have the grid. For bands computation, we actually specify what do we want in the bands.dat file. So এটা হচ্ছে gamma point 0 0 0. We want 40 of these points from 0 0 0 to 0.50 0.5. And that's our x that's our x point. Like in a particular kind of unit cell, there is a standard definition of xy, x, gamma, w, k points. I think I have the points. Yeah, I think I showed this document before, right? So there are standard definition of gamma x points, all the right here. So this is the unit cell in k space or reciprocal space. So along which path you move, that can be specified like this. Okay, that's how the k vector and fractional coordinates are related. Okay. So in Quantum Espresso, the input files, they only they take these fractional coordinates, but sometimes in the data file, the units can be in the Cartesian coordinate or inverse Armstrong units. So sometimes we need to convert back and forth between them. And once you know that it's just a matrix multiplication, things become easier. Okay. Questions? Okay. So let me stop sharing. What else? So I also wanted to discuss the density of states, um, but we don't have all of us here. Maybe we should discuss density of states. We shouldn't leave it for later. Okay. Let me join.